Hi, and welcome to a video for a Calculus 2 course at the beginning of the semester where we are reviewing U substitution integration. This is a video that's in kind of a series of videos, just getting you ready for all the integration you're going to see using U sub in your Calc 2 course. So let's get started. If I see a composition of functions, so by that I mean if I see a function like 1 plus x squared as a quantity inside of another function, so inside of the square root, when I'm trying to anti-differentiate that, I would just try U substitution first. Again, if you think if I were taking the derivative of this function, I would need to use chain rule to find the derivative, of course, and product rule the way it sits now. And if you need to use chain rule for any part of the derivative, you possibly are going to have to use U substitution for its antiderivative. So I'm going to go ahead and say let U be 1 plus x squared, so that's the innermost piece of my function within a function, again coming from that composition of functions. I will find du, so du is 2x dx. And then if I look at my antiderivative, that's exactly what I have. Here's 2x, here's dx. So those pieces, let's see if I can highlight these here blue for you. Since 2x dx is equivalent to du, that's what I will replace with du. And then I let the radicand, or the function underneath the square root, be my u. So I'm really just trying to integrate antiderivative here of u to the half du. So that's going to be add 1 to my exponent, u to the 3 halves, divide by 3 halves, which is the same thing as multiplying by 2/3. Of course, this was an indefinite integral, so don't forget your plus c. And now I will put my u back in. So my u was 1 plus x squared as a quantity, and there's my antiderivative. Okay, so let's try this again. So I can see in this next example here that I want to try U substitution again. Now I have a third root. That's okay. I have a third root, or a cube root, of the quantity. And I hope we do remember that we can't take square roots or cube roots or any power, whether it's a fractional exponent or whole exponent, to multiple terms. So for example, I cannot do this as, oh good, the square root of 9 is 3 and the square root of 16 is 4, because as we know, so that is not true, because 9 plus 16 is 25, so really I would have the square root of 25, which is 5. So it's not really a distributing of an exponent or power like we would think. I have to just take the square root of one term. Okay, so I'm going to let u be that 1 plus x cubed. Okay, so then my du is going to be 3x squared dx. And this is when we're going to have to take a look and see what we have in our numerator. Do we have the right power of x? So I do. I have the x squared dx portion of this. So that 5 doesn't really match exactly. Now, let's not work too hard. This 5 is a constant coefficient of my whole integral. So I'm going to rewrite just for a second here and pull this 5 out in front of my whole integral. Now you could also write 1 plus x cubed to the 1/3 at this point, if that makes it easier for you. So I'm just going to remove the 5, put it out in front because it is a constant coefficient of the entire integral. If you have more than one term, you may want to separate your antiderivative and do it term by term, so I can pull that 5 out front. But I think now you'll see where I'm going with this. I need 3x squared dx in order for it to match my du or be substituted with my du. So I'm going to multiply by 3 inside. Again, I need 3x squared dx. I have it now, right? I will replace that part with du, so all of that is going to become du. Well, you can't just multiply by 3 because you need a 3. I need to multiply by a factor of 1 so that I might be changing the way something temporarily appears, but I'm not changing its value. It's the same thing, we talked about this before, when you're adding fractions with unlike denominators. You might multiply this first fraction by 3 over 3 to get 3 over 6, so that when you add it to the 2 over 6, you have common denominators. You're not changing the value of that initial fraction, you're just changing the way it appears. So we can multiply by 1 as long as we also divide by that same value, because again, we have to multiply by 1. So I multiplied in a 3, so I will divide out a 3. So really what my antiderivative looks like is 5/3, and then it becomes du over u to the 1/3. Or in other words, 5/3 u to the negative 1/3 is what I'm antidifferentiating. So now I'm just using power rule. I will add 1 to that exponent. So if I add 3/3, I get positive 2/3. And instead of dividing by that 2/3, I will multiply by its reciprocal 3/2. And I should get 5/2 u to the 2/3, and so I'll put my u back in. My u was 1 plus x cubed. Okay? And again, I can check these because if I take the derivative of my answer, I should get that original integrand. Okay? All right. Next, let's look at a few more here. So let's look at trig. Well, again, this x cubed is a function inside of another function. So I'm going to let that piece be my u. I'm going to let u be x cubed. And then what you'll notice is du is 3x squared dx. And this is how you're going to know if your u substitution is the technique that's going to work. Well, it is here because I can see I already have the x squared dx. So I'm going to multiply a 3 inside of my integrand, or inside of that integral, and I will multiply by 1/3 outside my antiderivative. Again, I only have one term here, so I can pull the 1/3 out in front of the whole antiderivative. If you're integrating term by term, then that 1/3 only goes in front of the term that you multiplied by 3. So now what I have is 1/3 antiderivative. Well, I'll highlight this for you. This 3x squared and the dx is all going to become my du. And the sign of x cubed, well, x cubed was my u. So, okay, I will have inside my antiderivative sign of u. If you want to put that in parentheses, you can. So we should know the antiderivative of sine u is negative cosine of u. Again, plus c, because I'm an indefinite integral for right now. And because, again, the derivative of cosine of an angle would be negative sine of the angle, so that's where that negative comes from. And then I will put my u back in. My u was x cubed. So that substitution has to come back at the very end because your answer should be in terms of the same variable the problem was given in. Okay, let's do another one. So what I see when I look at this is some of you might see a product, like you have one factor of 6x cubed and another factor of that secant squared of x to the 4th dx. Well, maybe the factors are there because when you did the derivative, you had to use chain rule. Because remember, anytime you use chain rule, you're multiplying by the derivative of what was inside of your function. So I see x to the 4th inside of a trig function, so that's my angle. So I'm going to let u be that x to the 4th. And again, you're going to be able to tell pretty early on if this u substitution is going to work or not. Take a look at your du. Your du tells you whether this is going to work. I have 4x cubed dx. I can absolutely manufacture in a 4 if I have to, because I can multiply by 4 in one area and divide by 4 right outside of that, and then I'm really just multiplying by 1. So that's exactly what I need to do. I have the x cubed dx part, right? That's all going to become my du if I have a 4. Well, the 6 is not a 4. So I'm going to move the 6, and I'm going to put the 6 out in front, and then see if we can figure this out. Maybe you do this rewrite step, maybe not, but I'll kind of highlight what's becoming what. This x to the 4th is going to become my u, and then this x cubed, oops, that's way too dark. So this x cubed dx piece will become my du, but I need that 4. So I'm going to multiply inside by 4, because now I would have the whole du. So I multiplied in by 4, I will divide by 4 out front. Again, I have a single term that I'm integrating, so that does turn into be a constant coefficient of the whole problem. So outside of my antiderivative, I have 3 halves. All that yellow highlighted stuff is going to become my du, and then I'm just integrating secant squared of u. Well, we should know that the derivative of tangent of the angle gives me secant squared of the angle, and just don't forget your coefficient. I'll put my x to the 4th, substitute that in for u. So after I substitute in the x to the 4th for that u value, I am done. Okay, 2 more on this video, because hopefully you're finding that you are being refreshed with your u substitution, and so far it should be going pretty well. So if I have, again, I see in here I have a natural log of x function inside of cubing. So this goes back to your composition of functions, right? A function inside of another function. So natural log of x is inside that cubed. That's what I would start with for my u. So I'm going to let my u be natural log of x. And then you'll know if this is going to work or not based on your du. So my du will be the derivative of the argument, which is 1 over itself. Of course, don't forget you're with respect to x dx. All right, so literally that's exactly what I have. If you notice, your numerator is going to become your u cubed, and then this over x dx piece will become du. Well, I can integrate that all day long. That's just u to the 4th over 4, and this worked out beautiful. Don't forget your plus c, and don't forget to put your u back in. So my u was natural log of x. So again, my answer should be in terms of the same variable that my problem was given in. Okay, last one, and I'm actually going to do this one 2 different ways. So I'm going to give you 2 different options for trig, because trig is so amazing and it's manipulable, so you can do it, you know, using multiple techniques sometimes and end up with the same answer. I'm also going to show you in the end graphically. Those 2 answers don't look like they're the same, but I will show you why they are. So let's just look at option 1. Now, I'll say option A, because I don't want you to think that option 1 should be your go-to or option 2. It's literally whatever you see. So if you are adept to u substitution, because that's what you've been doing and that's kind of what you see, if you look at this antiderivative right here and say, hey, I know u could be cosine of x. If that's something that you're saying right away when you look at this, you see it, then option A is going to be for you. Okay? So if u is cosine, I can always write this antiderivative as over u cubed, right? You can always write your u to a power. So don't overcomplicate your u. You shouldn't have to use a chain rule upon a chain rule just to find the derivative of your u. That should be a pretty simple derivative to take. Now, because I can always write u to a power or u times something else. So, okay, u is cosine of x, so du is negative sine x dx. And this works out perfect if I throw a negative 1 in, so I'm going to multiply by negative 1 inside and a negative 1 outside. So I'll have a negative out in front of my antiderivative, and then the sine x dx piece that's in here is going to become du. So what I'm really anti-differentiating is u to the negative 3 du. Of course, don't forget that negative out front. So I'll do power rule. So I will add 1 to my exponent. So I do get negative 2. Be careful with that. You did have a negative out in front. So, when you do power rule, you added 1 to your exponent to get negative 2, then you divide by that same exponent. So just be careful with your negatives here. This should be a positive 1/2 u to the negative 2. I'm going to say one more be careful about. We do not write trig to a negative exponent. So I'm going to show you what I mean. I'm going to insert what my u represented. It represented cosine of x, and that quantity would be to the negative 2. Now specifically, if you see sine of x to the negative 1 like so, we did not want you to confuse a negative exponent with inverse. So specifically for trig, they got together and said, hey, that could be confusing, right? Is it a negative exponent and just a reciprocal, or is it inverse? So this last one here is representative of inverse sine. And as we know, sine, you're looking at sine of an angle will give you a side ratio, but inverse sine, this is the side ratio, right? X is your side ratio when you're solving for an angle, so it's exactly opposite. So what we did is we said, okay, this is equivalent to 1 over sine x, and so we gave that a name. So that's why every single trig function, sine, cosine, and tangent, all have a reciprocal name. So I'm not going to leave cosine of x to the negative 2. I'm going to rewrite this as secant of x, because really it looks like this. So you have two choices, I guess, for the final notation. Instead of reciprocating, cosine squared, you could write secant squared, or you could leave the cosine squared x in the denominator. But I really would suggest not leaving cosine of x to the negative 2. I think it gets a little bit confusing. But I think one of those final two answers would be acceptable. Okay? So I don't know if that little tidbit about raising trig to the negative 1 or negative 2 or negative 3 is something that you already knew. If it is, great. But I would definitely turn your negative exponent into a positive exponent or use the reciprocal name. All right, so I'm going to do the same problem again. Let me write it. And if you really thought, no, I know that u substitution, I'm good to go, then maybe this option B is not for you. Now option B, and again, there was no rhyme or reason to this order. Let's see if I can get them both on the same screen here. Option B just says, can I rewrite the trig? So maybe I have a natural derivative and antiderivative pairing in it. So meaning sine over one of those cosines is something. And then 1 over cosine squared, I can also rewrite. So just the names of these functions, right? So sine over cosine will give me tangent. So I have tangent of x. And the reciprocal of cosine squared x is secant squared of x. All, of course, dx. You may have been leaving off that dx in Calc 1. I'm going to tell you it's very, very important, especially the farther you go in calculus, because that tells you your variable of integration. So when we get into multivariable calculus, that will be huge, but also will tell us a lot as we progress through Calc 2 on what your sample slice looked like. So now I'm going to integrate tangent secant squared. I can do that with a simple u substitution. So maybe you see this, maybe you don't, but if u is tangent x, du is secant squared x. So I'll let u be tangent x, and my du is the leftover piece of that integrand, secant squared x dx. So I literally am integrating u du in this case. Okay, well that would be u squared over 2. Or I'll put my u back in. Your u is not the same as it was before. In this case, u is tangent of x. So I will say tangent squared x over 2 plus c. And now here's where I want to spend just 1 minute showing you the graphs of these two. Okay, if I look at these two graphs, I can kind of shift this down a little bit here. I'll notice that the red, I put in that answer, we got, second here, this tangent squared x over 2, and the original one, I just wrote it as 1 over 2 cosine squared of x, but I could certainly have written it as a half secant squared x as well. In your graphing calculator, you don't have a secant button, so you would have to write it as a reciprocal of cosine anyway, so that's why I did that here in Desmos. But Desmos does allow you to type in secant squared and cotangent squared, all that kind of stuff. Okay, so it does not appear that the blue graph is tracing the red graph. And if they're exactly the same, well, then the graph should be the same, right? They should trace each other. Why don't they? Well, look at our two answers that we have. Each of these two answers has something next to it. They each have a plus c. So if I shifted this red curve, which is my tangent squared x over 2, up just a little bit, then these two graphs would trace each other. So what that means is the c from my first option doesn't necessarily have to be the exact same number as the c from my second option. If you had a particular point that you know is on these curves, right? So maybe I know a particular point, then I could solve for each c value. And again, the c values are not going to be the same, but once you find those c values for that particular equation, they would absolutely trace each other. So the c's are where you get your vertical shift from. So I would take this point right here, 0, 0. And so if I shift up maybe a half, so if I add plus 0.5, now I can see that these graphs, right, trace each other. If I turn on and off the red, you can see that the blue graph is exactly covering the red graph. In other words, my tangent squared x over 2 plus a half is exactly the same as my g of x function. So what that means is the c values are exactly a half difference, and that's okay. So they do match. So I hope you found this video helpful. We went through, quite a few examples of some additional u substitution where it's going to work right away. We will take a look in the next video about some definite integrals with u substitution, trying to remember to change our bounds. So I hope this finds you well, and thanks for watching.